All right, we're live.
Okay. Hi, everyone, and thanks for tuning in into this week's Quantum Chaos 2020 seminar. So it's my great pleasure to introduce today's speakers, Pavel Kos, who will be talking about solvable chaotic many-body quantum systems. Pavel's a PhD student at the University of Ljubljana, where he's been working with Thomas Prozen and Bruno Bertini on a variety of interesting topics, and today he's going to be talking to us about those. All yours, Pavel.
Okay, welcome everybody. Thank you for the introduction and for this nice opportunity to present our work and also for organizing this series, which I really enjoy. So I will talk about solvable chaotic many-body quantum systems, and I will try to briefly go through the papers mentioned here. So let's first mention my collaborators. So this work was done together with Tomasz Procyn, who is my supervisor, and Bruno Bertini, who is a postdoc in our group. This was an exciting, and it still is an exciting collaboration. So let me start first with the introduction. So the main question that I will try to address, or that we were trying to answer in the recent years, is how to understand the behavior of some generic or chaotic quantum many-body systems. This is a difficult problem. First of all, if you just want to attack it directly, you can just make a exact diagonalization or direct simulation of, let's say, 15 sites or something like that. But actually, we would like to understand the behavior of really many-body physics out of equilibrium. And there have been recently a lot of results for free model and integrable models, but actually it turns out that even for the chaotic models, one can find solvable examples. So you can think of solvable examples as some sort of toy models, which show the behavior of a typical chaotic model. And it's very interesting area to try to study them and understand them. So first of all, the most well-known example is the example of random matrix theory, which goes back to Dyson. So the idea is if the evolution is governed by a random matrix, then one can obtain exact results about some questions for random matrix theory. Recently, this has made a very big progress in connection with so-called random unitary circuits, where you take random unitaries, but which are acting only locally on a few sites. But these are not the only examples. In this talk, I will talk about so-called dual unitary models. So these are models with a special property, which enables us to answer some questions exactly. And this can work even for clean systems, or sometimes also disordered, depending on the setting. Recently, we realized another class of solvable chaotic models, which we call no splittings, which was put in our recent paper, which I won't really mention, but I believe that there are more examples here, and this is an exciting new area of quantum many-body physics. And in this talk, I will think of how to characterize these chaotic models. And first of all, we will talk about the spectral characterization. So we look at the spectrum. And secondly, we will look at dynamical characterization of models. So one is interested in dynamical complexity, how the complexity, how we get and build complexity in our, let's say, quantum evolution. These examples are very relevant for studying non-equilibrium statistical mechanics, for condensed matter, for thermalization. Furthermore, there is a very close connection with quantum information. Let's say one recent example is the group of quantum simulators by Google's group. When they can now they have a quantum simulator of quite a lot of qubits, and they want to, let's say, know if they can really claim that they have performed some simulation which cannot be performed classically. So one is really interested in complexity of quantum evolution. So, and this is tightly connected with a chaotic evolution, with the fact that evolution is chaotic. And this is also has attracted a lot of interest in connection with high energy theory and quantum gravity, string theory, and black holes, and so on. Okay, so the plan for today is to focus more on the broader picture. So I will try to tell you more, but less precise. And I won't focus so much on the methods, but more on the general ideas. But I would also stress that the methods are still important, because in the end, you need to do the calculation to actually compute something exactly. So the plan is to first introduce the dual unitary models, which we will study. Then we will go on to spectral indicator of chaos, so-called spectral form factor. So we will discuss what it means that the model is chaotic according to the spectrum. And next, I will try to discuss that we also have another indicator of chaos, which is dynamical, and which we don't need the spectrum, and it's more local. And then in the fourth point, I will also try to discuss the correlation functions in these models, which can be computed exactly. And then I will repeat the main points. So what is our setting? Our setting will be a quantum circuit. So let's say that we will have 1 + 1 dimensional quantum circuit. So let's say that we have a spin chain, and for concreteness, we will focus on spin chain of spin 1/2. In principle, one can also study higher spins or more larger degrees of freedom per site. And we will study the circuit shown here. So basically, we will have sites at positions and at integer and half integers. And then we will evolve these sites by unitary gates, which couple 2 qubits. So first they will couple, let's say, 0 and 1/2. And this will be the first layer, first half-time step of our evolution. And then in next half-time step, we will evolve together the 2 other sides. So in this case, we get this quantum circuit, which couples all of the spins. And I will use this graphical notation of having these gates U with red and U dagger with blue. And let me stress here that if we have a case when all the gates are the same, as is shown here, this is a sort of a Floquet dynamics, because you can imagine that we have a layer of this layer of these small gates U, and then your time evolution just consists of repeating of the evolution with these gates. And we will denote this bigger whole evolution by this U mod BB, and it can be written in the following way. So we have just a tensor product of these gates, and then we have a tensor product of these gates, which are shifted by half a site. So this is our setting. And now let us define what dual unitary quantum circuits means. So the circuits are unitary because we have quantum evolution, closed quantum evolution, which means that U dagger or U dagger U is identity. And if we represent this graphically, it means that if we connect U dagger with U or U with U dagger, we just get straight lines, which are just identity. And moreover, in our dual unitary circuits, we demand another property to hold, which is basically if you connect U and U dagger sideways, you also get the identity. So if you connect U dagger and U dagger from this side, you also get the identity. And this U tilde is just reshuffled U in such a way that we change the incoming and outgoing indices. And this also means that if one writes a propagator in space instead of propagator in time, if we go back, one can imagine that these two layers will be a propagator in space. And the dual unitarity means that this propagator in space would be also unitary. And for spin 1/2, which couple two sides, we can write a generic dual unitary gate, which can be written in this form. So it consists of one qubit gate U plus minus V plus minus. And then we have a gate which is really coupling the two sides, which is this V of J, which is exponential of -I. And now the dual unitarity fixes the parameter in front of sigma x to be pi over 4. And also the same for the parameter in front of sigma y. But this third parameter is still free. And if one writes generic U4 gate, the only difference is that these two parameters are general. So dual unitarity only fixes two parameters out of many. So we still have a big manifold of dual unitary quantum gates. So let me show you one example, which might be easier or harder to understand depending on your background, and which I will also refer to later in the talk. And this is the example of self-dual kicked Ising spin chain. So this example consists of a spin chain, which is evolved in time steps. So we have a Floquet evolution, and the time steps consists of two parts. So we have a first part, which is Ising evolution, which is written here with this parameter fixed to power 4. So it's self-dual. And then in the second part, we make a kick in the x direction. We apply a magnetic field in the transversal direction. And maybe I didn't stress before, in this first part, we had a magnetic field in the z direction. And this magnetic field can be uniform, or also a lot of results carry over if this magnetic field is random or disordered. And this self-dual kicked Ising can be written in the circuit form, which I was showing before. If you're interested, I can show you at the end. It's not so important. So this is just like a concrete example to have in mind. Okay, so with this, I introduced the models that we will be discussing. And let me now go to the spectral indicators of chaos. So let's say that we have time periodic evolution, a Floquet evolution. So it means that after some time big T, the Hamiltonian repeats itself. And this means that we have a Floquet evolution. And this Floquet evolution has a Floquet operator of one period, which is, I mean, in our case, we showed it before what it was concretely. And this, if one looks at the spectrum of this Floquet operator, one finds that the spectrum consists of e to the I phi n numbers. And then we have quasi-energies phi n, which go from 0 to 2 pi. And we can study this spectrum of quasi-energies. And it's very similar to studying the spectrum of time-independent Hamiltonian systems. And if one looks at this spectrum and let's say draws it on the line, one can see a clear difference between free models, which will show, let's say, periodic spectrum, integrable models, which will have energy levels which are basically random anywhere, and chaotical models. And chaotical models show level repulsion. So first thing which you see in this picture of universality is that you don't have so many energy levels which are close together. And this is a strong indicator that your model is chaotic. Moreover, this can and often is used as a definition of that a model is chaotic for a many-body quantum system. And this is a famous quantum chaos conjecture, which states that the model, quantum model is chaotic if and only if the spectrum is well described by a random matrix theory. And there are very nice connections, which were shown in these works, which basically show that if you have a model which have a well-defined semi-classical limit, if you have a semi-classical limit which is chaotic, which has positive Lyapunov exponent, then your spectrum is well described by a random matrix theory. We wish to characterize this spectrum, and I mean the spectrum is a huge object, it has exponentially many numbers, and we wish to characterize the spectrum and the universality of the spectrum using some indicators, and then I will discuss the so-called spectral form factor, which is simple quantity which you get out of the spectrum, and you can check it and see if your model is chaotic or not according to spectrum. And the spectral form factor is a Fourier transform of the 2-point correlation functions of energy levels. So you look at your spectrum, then you look at 2-point correlation between the energy levels, and then it turns out that it's convenient to do a Fourier transform of these 2-point correlation functions. And this is a very nice object. Also, these semi-classical connections were made exactly for the spectral form factor. And the spectral form factor can be expressed in the following way. So one can write the formal definition, which I explained to you before, and then one sees that it can be written as a trace of your propagator u to the t, absolute value squared. And this is a very nice object. It is basically a partition function in imaginary temperature. If you think about it, usually when you talk about partition function in the in statistical physics, you have trace of e to the minus beta h. Now you have trace of e to the I ht, let's say. And it's a very nice object, and it's the most suitable indicator of chaos of spectrum for analytical treatment. And it looks something like this. So let me just, okay, so here is the picture how it looks like. So we have k of t, and if we have an integrable model, then we just see basically a straight line at the value of 2 to the L, so an exponentially large value of the spectral form factor. Then on the other hand side, if we look at the random matrix theory, then we have this red curve, which starts basically from 0 and has initial linear slope, and then approaches the saturation at the Heisenberg time, which is very long time of 2 to the L. Then, typical chaotical system behaves as this blue line. So it has a very short deviations from the random matrix theory, which can be exponentially large deviations. But then after some time, it starts to follow random matrix theory. And this time, which we will call the taueless time, or it's sometimes also referred to as a Ehrenfest time, is basically the time where the spectral form factor starts to follow random matrix theory prediction. And one can understand it that this is 1 over correlation length in the spectrum. So if you have some model which is not random matrix theory, which is not really a random matrix, then at some very large distances in your spectrum, you will lose the correlation. And this correlation, this point where you start to lose your correlation is 1 over taueless time. And this is, in some sense, an indicator how chaotic is your system. Because if it has a very long taueless time, it means that it's not, it's not really that chaotic. You will only see, maybe you will see level repulsion, but at longer distances in the spectrum, you won't see the random matrix theory behavior. And what is interesting is that for dual unitary models, it seems that this taueless time is of order 0. We basically see random matrix theory from time 0, which is very surprising. And what is even more surprising is that we were able to prove it for the dual unitary kick teasing, which was quite a non-trivial time. task, quite a non-trivial task, for which we used the algebraic properties of suitable transfer matrix. And yes, and because this Thouless time is of order 1, we can say that this dual unitary kick teasing is in some sense maximally chaotic according to the spectral indicator of chaos. And there are also interesting recent results about the random Floquet circuits. So if we have a Floquet evolution, which has a random gates in it, and then one average over gates, then one sees that one gets logarithm L Thouless time. So Thouless time, which scales as logarithm of L. And we also saw that in the kick teasing with longer range interactions. Instead, if one has conservation laws, and let's say that one sees diffusion, then one sees a Thouless time which is of L squared, and which is consistent with diffusion. It's the time which it takes for system to see that we get information from one end to the other. Okay, so this was a short introduction into the spectral indicator of chaos. But now we would wish to have some indicators of complexity, or some indicators of chaos which are dynamical in nature. So what if we don't have access to the spectrum, or if we only can access our system locally and we wish to take the thermodynamic limit, we wish to find some indicator of chaos which will agree with a spectral indicator of chaos. We will look at the evolution of the local operators. So basically we will start with some local operator A, traceless operator, then we will evolve it in time. It will evolve inside the light cone, it will spread, but it will also get complicated. It will become a superposition of many operators. And then at some time, we wish to see how complicated these operators are by basically looking at the entanglement entropy of this operator. So we will vectorize the operator, we will think of operator as a vector, and then compute the entanglement entropy with the rest of the system. We will forget about the rest of the system, trace over it, and then see what kind of entanglement entropy we get. Okay, let me see how. Okay, so I'm doing well with time. So we wish to characterize the complexity of the dynamics and really to distinguish the chaotical behavior according to spectrum and integrable and free dynamics, which we can also detect using spectrum. And this idea of operator entanglement evolution is quite similar to the idea of autox. Autox, this is more common for the experts about autox. So it's autox mean out of time ordered correlators, and they attracted a lot of attention recently. And autox are a very interesting object which tells you about how your operators spread inside your light cone. But they don't really measure how complex your operators are. So you can have a very simple operator which doesn't have any superposition of different operators, and it will show a autoc which can be indistinguishable from a chaotical, from a model which will have very complicated operator. And yeah, and the results from the autocs, at least to my knowledge, do not agree with spectral definition of chaos. So that's why we will focus on a similar but different measure, which is called operator entanglement evolution of local operators. This operator entanglement entropy measures how hard it is to classically simulate the evolution of your operators. So it measures how quickly the bond dimensions of the matrix product of MPO, matrix ansatz for the operator, how quickly these bond dimensions grow. So if one uses MPO methods to simulate operators, how hard is it to classically simulate? Let me just quickly mention that yeah, the question about autox in dual unitary circuits was also studied in this paper by one of our co-organizers, and they show that autocs in dual unitary circuits spread with maximal velocity. Okay, going back to operator entanglement entropy, one sees linear growth of operator entanglement entropy in chaotic models. This was shown numerically before and conjectured, and this is what one expects, that one has this exponential hardness of quantum simulation. And also in random unitary circuits, it was also calculated that you get shown how you can understand it and calculate it. But in the free or integrable models, one sees saturation or logarithmic growth. And there have been papers so a long time ago about free models, but then recently there have been works about integrable models showing logarithmic growth of operator entanglement entropy. Okay, so let's go now to the question how to calculate operator entanglement entropy in our case. So we will draw some pictures, basically. So first we look at we write the evolution of our operator in the Heisenberg picture. So we have this u to the power t and u dagger to the power t and our operator in between. And then we will first fold the circuit. So we basically put this red part behind the blue part, and we get a folded circuit like this. And we will have now these double gates, and also our identity operators here become just these empty bullets, and our operator A becomes this black bullet and vector A. So we also made a vectorization. Okay, and next we will simplify our circuit using unitarity. Because of unitarity, this part is basically just white bullet. So we get a light cone emerging from our operator. And so we get the evolution of our operator, which is this light cone. And next, now we have this our vector here, which we wish to characterize how complicated it is. And for this, we calculate the Rayleigh entanglement entropy. So Rayleigh entropies are defined in the following way. So basically, we need to calculate traces over the powers of the reduced density matrices. So let's first see how we get a reduced density matrix. We have our operator, which is our kit, but we also need the bra part. So we get this part, which is complex conjugated. Then we trace over the part of the system which we wish to forget. So we trace is just connecting these two parts. And now we have our reduced density matrix. Then we take a second power of reduced density matrix. We get another copy. And because we multiply the two, we connect the two. And then we take the last trace and we connect the indices which have been open. And we are left with an object like this. And then we use graphical rules for simplification of this object, which basically we will use unitarity of double gates. So we will connect this part and this part. We'll simplify this part and this part. So we will end up with a part which will look like this and like this. And when we simplify and rearrange, we end up with an object like this. So now we used a graphical way of thinking, graphical rules, which really help a lot. If one would need to write this down without the graphical notation, it would be much harder. But using this notation, we arrived at some very nice object. So now again, you can think that we have a sort of a partition function with a special boundary condition, and it's a bit non-uniform. And furthermore, it's not a classical statistical mechanics, but it's quantum statistical mechanics in a sense, because we have complex numbers. So one cannot perform efficiently, let's say, Monte Carlo simulations or something like that. And now we have this object, and the main idea how to progress from this point. So, okay, so at this point, let's say I haven't used dual unitarity at all. for this object, one can write this object for any model. But now we will use the dual unitarity, and we will use it by examining the transfer matrix. So dual unitarity can help us finding the leading left and right eigenvectors of the transfer matrix. So to get back, if we wish to evaluate this object, then if t plus y or t minus y goes to infinity, so yeah, if either of the sizes goes to infinity, then we can use only the leading eigenvector of the transfer matrix, and we can know which we can figure out which are the leading left and right eigenvectors for dual unitary models. And they basically consist of having all these empty bullets, so basically identity matrices. And one can quite easily see that they are eigenvectors, because if you put here a white bullet, this will just become a white bullet here and a white bullet here because of dual unitarity. Maybe it's a bit faster this, but believe me, and you can check the paper if you wish. And then there are other eigenvectors which correspond of having these identities, and then connecting the sides of this gate and the transpose and the complex conjugate gate. So we connect these two parts and these two parts, and if we connect these two parts, then this thing simplifies. Okay, so because we know the leading leading eigenvectors, we can just and leading eigenvalue, we can just use projection to the leading subspace, and we can evaluate the operator entanglement entropy when t plus x or t minus x go to infinity. So x is here the position of the operator, and if we leave the cut at the same position. What we see is linear growth of operator entanglement entropy, which we expect for chaotic models. And it's shown here. So here I'm just plotting the slope. And let's focus on the green curve, which is the Rainy 2 entanglement entropy. And we see that we have a green curve here. And here the slope is actually maximal. And this is an interesting point, that these dual unitary circuits are in some sense maximally chaotic also with respect to this indicator of chaos, not only the spectral indicator of chaos. But then when one increases the J parameter, then this slope decreases. And one interesting point is here, when J is equal to pi over 4, then our dual unitary gate becomes basically a swap gate. So then we don't expect any chaotic behavior. And what is also interesting is that the slope in the random unitary circuits is roughly half of the maximal. So if you just take random gates, you will have a slope, you will get linear growth, but with a slope which is roughly half of the maximal. Okay, so this was complex, a dynamical indicator of chaos. And it's very nice that it seems to agree with a spectral indicator of chaos. But now we wish to characterize these dual unitary models in more detail. So we will look at the correlation functions. We are interested in correlation functions on top of the infinite temperature state. And I want to show you the results on this because of few parts. First of all, you will see the strength of graphical thinking, because just by applying graphical rules, you can basically get the correlation functions. And then we can also see that these dual unitary models can exhibit different level of ergodicity according to correlation functions. And lastly, one can also access models which are away from dual unitary models. So one does a perturbation, and one can also calculate the correlation functions in these models, which are, let's say, more general. So we look at the correlation functions. We have our graphical rules of unitarity and dual unitarity. We depict the correlation functions with a with a diagram. So we have this evolution of our operator, and then we put the operator at the end. Then we first use the unitarity, and we get our light cone. And next, we use the dual unitarity, so we can simplify this gate with this gate, and later this gate with this gate. And then one gets a circuit like this. So then one sees if one doesn't have the operator at the end side, one gets this initial operator, which is connected to itself. So it's basically trace of the initial operator. And if the initial operator is traceless, then the correlation functions are inside the light cone are 0. And one expects this because if you think about it, let me go here. If you think about it, here we simplified our evolution to a light cone using unitarity, but because we have unitarity in the space direction, in this direction, one needs to be inside this light cone. So the only part which is inside this light cone and this light cone is just this light ray. So this is the only position when one gets non-zero correlators. So one just gets that correlations are exactly 0, except if the operator is at the light ray, and they are written in this simple circuit, and they can be expressed using a completely positive trace preserving unital map, which is shown here. So unital just means that if we evolve identity, the identity will just evolve to identity, which is what we expect. But this map has 3 other eigenvalues. You can think that it evolves some linear combination of operators sigma x, sigma y, and sigma z. And then the correlation functions are just written in this simple form. So one just starts with the operator, then applies this map, which one can write as a 4x4 matrix, take the power of 2t, and then contract with the ending operator, and one gets the correlation functions. And it's not necessarily that one starts with infinite temperature initial states. There was also a generalization recently for if one starts from a class of solvable initial states. Let me discuss quickly the behavior of this correlation function. So even though we have dual unitary models, we have these 3 non-trivial eigenvalues of this matrix M. And based on these eigenvalues, we have 4 different types of ergodic behavior. First of all eigenvalues can be equal to 1, and then the correlations are just constant, and we can think that we have non-interacting behavior. Furthermore, it can happen that only, let's say, one additional eigenvalue is 1, so just which means that just some correlations are constant. So we have non-ergodic behavior. Then what can also happen is that all eigenvalues, or some eigenvalues are of absolute size 1, but they are actually complex. So if one looks at the correlations don't decay, but their average goes to 0. So one has behavior which is ergodic, but it's not mixing. Or what typically happens, what generically happens, is that all these 3 additional eigenvalues are smaller than 1 in absolute value. So then all correlation functions decay exponentially to 0, and we see ergodic and mixing behavior. Okay, and now we saw this rich behavior in dual unitary models, but let's go now on and perturb this dual unitary model. So here is the picture how the correlations look like in the perturbed dual unitary models. And we see this light ray, which comes from dual unitarity. But furthermore, now we have much more generic behavior because we have correlations inside the light cone, which we expect for generic systems. And what is interesting is that these correlations are proportional to the perturbation. So it means that dual unitary models are stable starting points for perturbation theory. Perturbation theory works. And I will quickly describe the idea how one can actually calculate the correlation functions in perturbed dual unitary models. And okay, so we start with our correlation functions. And I will show you correlation functions in the folded picture. So if you think of the diagrams I was showing before, they are now folded. And we have the operator here. Then we evolve it with the folded picture. And then we have AND operator here. And now we use the simplification of unitarity here. So we got rid of this part because we have light cone emerging from the initial operator. Furthermore, we have also light cone going backwards from the final operator. So we have this sort of correlation functions. And now the idea is that one can expand the correlation functions as a correlation functions of dual unitary part of the circuit and defect part of the circuit. So this is a bit non-trivial, and I'm going a bit quickly here. But the point is that what happens is that your, let's say, operator, they travel along a light ray, and then they encounter a defect. Let's say they encounter a defect here, and then they change position, and then they go straight, and then they encounter a defect, and they go straight. And so you get like one-dimensional path connecting your initial operator and final operator. And the contribution of this path is proportional. So we get, for each defect, we get proportionality to the perturbation strength. So if we have a weak perturbation, then the contributions which have just, let's say, two defects will dominate. So the contribution where we have one defect here, we go here, one defect here, and go here. These are the contributions which will dominate. But which we can write some formula of all these one-dimensional paths. And it turns out that this works very well to describe the correlation functions in perturbed dual unitary models. Of course, what can happen is that sometimes like this line would be ticked, so we would have another gate here and another gate here, but this is suppressed. Okay, so I went quite quickly here, but the idea is that one can write an efficient formula for calculating correlation functions in perturbed dual unitary models, and these dual unitary models are stable with respect to perturbation. And each of these paths can be easily evaluated. It's just a product of 2 to the t of 4x4 matrices. It's similar to the case before, but now we need to evaluate all of these different paths. And we can get a closed form formula for correlation functions. And furthermore, we found some interesting non-dual unitary solvable cases. But let me not go into this right now, since I'm running out of time. And let me just make a summary of the most important points. So the main point I wish you to take is that exact solutions in chaotic models are possible. And this was quite surprising for me. Before I started my PhD, I didn't expect it. But to get exact solutions, it seems that one needs something. One either needs dual unitarity, which I was explaining to you in this talk, or one needs to average over randomness, or something else, some non-trivial condition. In this talk, I tried to convince you that the methods of graphical rules and analysis of transfer matrices are very strong methods to get exact results. And these are basically the main methods which we use. Furthermore, I introduced the spectral indicator of chaos spectral form factor. Then I described you the dynamical indicator of chaos, the entanglement entropy of local operators. And according to these two indicators, it seems that dual unitary circuits are maximally chaotic and solvable in some sense. Then I described the correlation functions in dual unitary models, and lastly, I was describing the correlation functions of perturbed dual unitary models. And with this, I'm going to conclude, and I will be happy to answer your questions. Thank you.
Thank you, Pavel. That was great. I really enjoyed the talk personally, and particularly the description of all these approaches to quantifying chaos. And so let's see if we have questions already. As usual, I like to abuse my position and make one of my own. So I'll start with that. I was curious when you were showing how the operator entanglement entropy, the result for the slope for the growth rate of this linear growth, right? That you said that for the case of high random unitaries, the growth was still linear, but it was slower. Is that?
Yeah.
Did I got that right? Okay. Is there? I don't know. For some reason in my head, it kind of seemed like unexpected. Or, I mean, do you have any intuition as to why these high random unitaries would have a slower growth than these kind of kicked Ising circuits?
Okay, yeah, I think that's an interesting question, I must say that I was also surprised when, just for comparison, I just ran the numerics for the random unitaries, and I saw that the slope is actually not maximal. And it seems that if we just randomly sample gates, some of these gates are not really chaotic enough. And it seems that in some sense, there are enough of these gates which are not making the operators complicated enough. So what we wish at the end is to have a really operators which spread through all parts inside the light cone. Mm-hmm. And also they became really complicated inside the light cone. So there might be two parts here actually. So one part is the speed with which operators spread in the random unitary circuits, the so-called butterfly velocity. I think it might be smaller than the maximal already. So it might come from the fact that basically the operators are not spreading at the maximal velocity. And I think that would be the main reason.
I see. Okay, thanks. All right. So, well, we have some nice comments in the talk, in the chat, saying excellent talk and giving a round of applause. We have a few questions. Anatoly is asking, is there a sense that the eigenstates, eigenvalues of the products of such unitaries satisfy random matrix theory statistics?
So that can you please repeat the question? So the unitaries, the dual unitaries, or the random?
Sorry. So is there a sense, I guess, in which the eigenstates or eigenvalues of the products of such unitaries, that's what it said, would satisfy random matrix theory statistics?
Yes. Yeah. So okay, if I understand the question correctly, it's asking about the products of unitaries of dual unitary evolution.
That's what I understood too.
Yeah, if we have a clean evolution, then we are basically describing this precisely with the spectral form factor that we were computing. Of course, the spectral form factor is not the whole story. It's just has information about two-point correlation of the energy levels. Then one can also look at fluctuations of the spectral form factor. And what it turns out is actually that, it surprised us that for this case of self-dual kick teasing, the fluctuations are actually larger than one would expect from the simple random matrix theory for the matrices which are time reversal, which are compatible with time reversal. And the reason for that is that especially just for the self-dual kick-teasing, not for dual unitary circuits in general, then we actually realized that the correct random matrix theory ensemble is slightly different random matrix theory ensemble. If the question, but there is also a different way how to understand Anatoly's question is, what if these products of these dual unitary circuits are different? So we have time-dependent evolution. So let's say that we have evolution which is time-dependent, but it's always of dual unitary circuits. And one can also look at the eigenvalues of the operator of this time-dependent evolution, and this is actually a work in progress. So this is we will start to write a paper soon about looking at the spectrum of this time-dependent evolution.
Right, nice. Next question is, does the model have a 2D version? And if it does, is it solvable?
Okay, yeah, so that's an interesting question. So for the dual unitary, yeah, if one looks at the correlation functions in the 2D of dual unitary model, it's again solvable. And you again see there's correlations traveling along light rays. And it's a very nice exercise how to get it, and it carries over to basically any dimension, at least for the correlation functions. And it's it's quite nice, but I think we just mentioned it a bit in the paper, but there haven't been any more works in this direction. But I think it's definitely something we or somebody else should look at in the future.
Very nice. And then there's a question, kind of asking for a recommendation. Well, the question is, where do the graphical rules come from? And if you could recommend some kind of reference or literature on them, maybe your own papers.
Okay. So this intuition of graphical rules, I think it's quite connected to the area of matrix product states, matrix product operators. They're using a lot of this graphical notation. But also, the questioner can look at our papers. So, I mean, the graphical rules that we were using are very simple. We were basically just using the unitarity, the dual unitarity, and then the way how to, let's say, construct objects for, let's say, operator entanglement entropy, or one can use similar rules to calculate even entanglement entropy after a quench. So in the end, I think they are quite simple. So at least the ones that we use. And I think the best idea is just to try to rederive some of calculations that you see in some paper using pencil and paper or iPad, and just contract things. One needs a bit of time, but then it really becomes easier to think in this way.
All right. Okay. Well, thank you very much for answering the questions. And I think that's all of the questions for now.
Actually,
and so, yes, go ahead.
I might abuse the fact that I'm still in the call to also ask an additional question. So for dual unitaries, if you look at the correlation functions, you can have both ergodic and non-ergodic behavior. But I would also expect this difference in ergodic and non-ergodic behavior to show up in the spectral form factor. So does something special happen there if you're looking at non-ergodic but dual unitary circuits?
Okay, yeah, that's a very good and accepted observation. And the fact is that I didn't go so much into the actual procedure how one calculates the spectral form factor. So we actually just calculated the spectral form factor for the self-dual kick-teasing, which is at j equal 0, which is in some sense the most chaotic one. But still, even at the self-dual kick-teasing, one can put all these magnetic fields to 0, and one gets a transfer field Ising, which is a free model. Okay. So let me just find this. Okay. So one can put all these H, J magnetic fields in Z direction to 0, and one gets a free model. The point is that how we calculated the spectral form factor for the kick teasing is that we introduced a sort of average over these magnetic fields. And then at the end, we send this the width of this average to 0. And we needed to introduce some sort of averaging because the spectral form factor is actually not self-averaging. So if one wishes to calculate spectral form factor, if one just calculates it, it's just a distribution, and one is usually interested in the mean of this distribution. And to get the mean, one needs to average, let's say, over time or over some parameter of your model, let's say this HJ parameter. And if you would instead just put HJ to 0 and calculate the spectrum of this model, you wouldn't see the spectral form factor, which shows the random matrix theory. Actually, you can do it exactly, and you see just some wild oscillation. Because it's a free model, it's not even just a Poisson, constant Poisson, but it's something very big and oscillating.
Okay, thanks. Back to you, Pavel.
All right. Awesome. Okay, so with that, we thank you again, Pavel, for this fantastic talk, and we thank all of the people watching on the other side. Thank you for tuning in. Before we leave, I'll just announce the talk that we have next week. So next week we'll have an experimental talk, which is going to be delivered by Gonzalo Alvarez from the Atomic Center Bariloche. And Gonzalo is going to talk about decoherence and scaling transition in the dynamics of quantum information scrambling. And so we're looking forward to that and to seeing you all next week here. Thank you.
Thank you.